The object at the center of this case never exploded. Its thin nickel covering stayed intact, and no mushroom cloud ever rose above Los Alamos. Even so, a plutonium core weighing 6.2 kilograms was involved in 2 separate laboratory accidents that killed 2 young scientists within 9 months of each other. On August 21, 1945, Harry Daghlian took a fatal radiation dose during an experiment with tungsten carbide bricks. On May 21, 1946, Louis Slotin took another one while demonstrating a different experiment around the same core. The name Demon Core came much later, and it has stuck better than the details have. The core was not cursed, and nobody banned nuclear science afterward. What killed these 2 men was a laboratory practice that walked a fissile core up to the edge of a runaway chain reaction by hand, so that a dropped block or a slipping screwdriver was all that stood between a routine measurement and a lethal dose. Welcome to History Case Files, where we reopen historical cases through the records they left behind. This file follows the evidence behind 2 deaths. Why did manual work continue after the first accident, and what changed after the second? Most of that can be answered from the timeline and the experimental setup, though the surviving record has limits. Private conversations and motives that were never written down stay unknown. Harry Daghlian was 24 when he joined the Manhattan Project's criticality work at Los Alamos. The National Park Service records that he studied at the Massachusetts Institute of Technology and Purdue University before joining Project Y. He helped transport the plutonium core to the Trinity site and was there for the test in July of 1945. Weeks later, the war had ended, though the work on nuclear materials carried on, and Daghlian was assigned to a criticality experiment at the remote Omega site near Los Alamos. On the night of August 21, 1945, Daghlian was building a neutron reflector around the plutonium sphere. The reflector was made of tungsten carbide bricks weighing about 4.4 kilograms each. He stacked them around the core by hand, adding material and watching how the neutron instruments responded. Nobody was building a bomb that night. The point was to find out how the reflector shifted the threshold at which the system would go critical. Every brick he added sent more neutrons back toward the plutonium and moved the assembly nearer to that threshold. The core itself was a small sphere of plutonium alloy, a fissile material that can sustain a chain reaction under the right conditions. How dangerous it was on any given day depended on what sat around it. Change the surrounding material or the geometry, close up the gaps, send enough escaping neutrons back into the metal, and the same core moves closer to criticality. Neither accident happened because the core decided to react. Both happened because people were deliberately testing how close a system could be pushed toward the critical point. That context is easy to lose, partly because the nickname came later and partly because the word plutonium goes straight to bombs in most people's heads. Los Alamos scientists needed measurements of how fissile material behaved for weapons work. One of the central questions was how much material in what arrangement would let a chain reaction keep itself going. The experiments were dangerous for exactly that reason. The answer sat at the boundary between an arrangement that stayed subcritical and one where a self-sustaining reaction could start, and one way Los Alamos obtained those measurements was by working near that boundary. The official accounts call these events criticality excursions. The phrase is technical, but the idea underneath it is simple. A plutonium atom absorbs a neutron and splits, releasing energy along with more neutrons. If enough of those neutrons cause further fissions, you get another generation. In a subcritical arrangement, too many neutrons escape or get absorbed without continuing the sequence, and the chain fades out. At criticality, each generation produces, on average, the next one. In a supercritical arrangement, the number of fissions climbs fast. Supercritical does not mean a bomb went off. It describes a configuration where the chain reaction grows instead of dying away. Very small physical changes can decide which of those states you are in. A neutron reflector is material placed around a fissile core to bounce some of the escaping neutrons back toward it. And that return traffic makes further fissions more likely. Tungsten carbide worked as a reflector in Daghlian's experiment. Beryllium did the same job in Slotin's. The hazard came from arranging a reflector around plutonium in a way that ate up the margin, keeping the assembly subcritical. In the mid-1940s, those margins were sometimes measured by hand. A researcher added reflector material in steps, watched the neutron response, and stopped short of the dangerous point. That called for precise movement, careful reading of the instruments, and, above all, a reliable way to back out. It also put the experimenter right next to the material, which meant his own reaction time was doing the work a safety device should have been doing. The first fatal accident showed how little room that left. The laboratory record, as summarized by the National Park Service and the Department of Energy Criticality Review, points to the final brick. The neutron indicators showed that putting it in its planned position would carry the assembly into a critical condition. So Daghlian started to withdraw it. Partway through that movement, the brick slipped and fell into the assembly. The arrangement went supercritical and produced a short, intense burst of neutron and gamma radiation. The event itself lasted moments. Daghlian first tried to knock the brick away, and when that failed, he pulled apart enough of the surrounding reflector to stop the reaction. Nothing detonated. The core's nickel covering held, and no equipment was destroyed. But the radiation pulse had already reached everyone near the assembly, and Daghlian, working at arm's length, absorbed by far the largest share of it. A guard was also at Omega Site that night, present but not assisting with the experiment, and there is no reason to build a rescue scene out of that. The records are clear that Daghlian was doing the reflector work himself. The safety lesson that came out of it was not that an extra observer could have prevented the accident, but that no single person should be the only active control over a near-critical assembly. A second person can question a step, read an instrument, or go for help, which is worth something. It still does not do what engineering safeguards do, which is remove the need for anybody's hand to make the final correction. Daghlian was treated after the exposure and died on September 15th, 1945, 25 days later. The National Park Service identifies his death as the first known laboratory fatality caused by radiation exposure. That he did not die in the room matters because it corrects a common version of the story. Neither of these men dropped where he stood, the way the retellings tend to suggest. Both suffered radiation injuries from a criticality excursion that was over in an instant, and the fact that nothing blew up did not make the event harmless. Mass is only one part of the equation, and arrangement is the rest of it. A compact shape holds on to more neutrons than a scattered one. A reflector around the outside changes the result without a gram of extra plutonium. Even the width of a gap between two parts can decide the outcome. Criticality safety is therefore not a question of memorizing one dangerous number. It means controlling a whole set of variables and keeping a visible margin between where you are and the point where the system can go critical. The warning signs had limits of their own, Instruments could show that the assembly was approaching a dangerous point, but an indicator cannot move a brick or hold a reflector apart. A scientist watching a count climb still needs distance and mechanical control to make the next movement safely. In Daghlian's setup, the corrective action had to be immediate and physical. In Slotin's, a hand tool was holding the critical gap open. Instruments made the risk measurable without making either setup fail-safe, and knowing that a hazard exists is a long way from building a system that cannot cross the hazard line on one ordinary mistake. None of this means that every experiment involving plutonium was doomed. What the accident proved was narrower. One particular arrangement carried a risk that careful intention could not manage. Daghlian knew the final brick would take the system critical, which is why he was pulling it back out. The fatal change happened while he was doing the safe thing. That single detail rules out the tidy explanation that somebody ignored the readings. The problem was a procedure that could go from a controlled approach to a radiation burst faster than the operator could recover from a simple loss of control. For the laboratory, that should have redefined what counted as a successful experiment. Getting the measurement was no longer the whole job. A safe method had to guarantee that an error would not turn the nearest person into the emergency shutdown. The first accident made that requirement visible, but it did not hand anyone a finished facility or the equipment and procedures to go with it. The months between the two deaths are the uncomfortable part of the story. The technical solution was being talked about while the hazardous manual practice stayed on the table. Several failures showed up at once in that first accident. A hands-on method put a scientist next to a fissile core, and the whole experiment depended on small objects being moved accurately. The final safety margin could disappear because one brick fell. Worst of all, the fastest response to an error had to come from the same person absorbing the radiation. Daghlian did stop the reaction, but he stopped it by taking the reflector apart at arm's length, which says everything about how the arrangement was built. It would be easy to flatten the next stage into an accusation. A man died, and the laboratory ignored it. The surviving evidence does not support that. Safety procedures were revised after Daghlian's accident, and the National Park Service records a new requirement that at least 2 people be present for this kind of work. Discussion and design work on remote-controlled test equipment started. Those were real changes. They also did not finish the job. A rule about how many people stand in the room does not conjure a remote machine. Facilities had to be designed and built, instruments arranged, operating procedures written, and all of that took time. The full chain of internal decisions that allowed another close manual demonstration before the remote equipment was ready has not survived in the public record. Inventing a secret order or assigning motives the documents do not support would be a cheat. The confident statement is plainer than that. After the first fatal accident, manual work near criticality had still not been eliminated. That gap between a lesson recognized and a safeguard finished is where this case sits. On paper, the hazard was understood. In practice, another method still put a researcher's hands next to the same plutonium sphere. The material around the core would change, and so would the immediate mistake. But the vulnerable part of the design stayed exactly where it was. 9 months to the day after Daghlian's accident, the same core went into another manual experiment. Louis Slotin had far more experience than Daghlian with the assembly work around early nuclear weapons research. Born in Winnipeg, Canada, he studied in Manitoba and in London before joining the Manhattan Project. At Los Alamos, he worked in the weapon physics division and had a reputation for practical skill. including the assembly of the first atomic device tested at Trinity. The National Park Service describes him as one of the people running criticality tests to establish critical mass values for uranium and plutonium. His experience made him the person demonstrating the technique that day. It says nothing about whether the method itself was safe. By May of 1946, Slotin was getting ready to leave Los Alamos and go back to teaching. And before he went, he was training others in a criticality technique. Several colleagues were in the room on May 21st when he demonstrated it. The requirement introduced after Daghlian's accident that more than one person be present had been met. Having people in the room, though, is not the same as keeping them at a distance. They were watching a procedure whose decisive control still came down to the movement of one man's hand. The reflector this time was beryllium instead of tungsten carbide. 2 beryllium half-spheres were set around the plutonium core, and as the upper shell came down toward the lower one, more neutrons would be reflected back into the core. The aim was to close the gap in a controlled way while watching how the system responded. The technical review later reconstructed the arrangement, and it is worth remembering that those figures are reconstructions rather than photographs of the accident. What they show is the principle: a plutonium core inside a reflector that turns dangerously effective once the halves get too close. The method used that day rested one edge of the upper beryllium shell against the lower shell and kept the opposite edge apart with the blade of a screwdriver. That screwdriver gap was the safety margin. Nothing would stop the shells from closing if it failed, since there was no automatic interlock and no remote mechanism keeping a person out of the radiation field. The procedure depended on Slotin holding the upper reflector in place and keeping the gap open by hand. Stated that plainly, it is hard to shrug off. There was no protective shielding and no machine that could be shut down from a control room at a distance. A screwdriver was the only thing keeping a beryllium reflector from closing into a nearly complete shell around plutonium. This is why early criticality work came to be known as tickling the dragon's tail. The phrase stuck because it was honest about the risk, which is not the same as doing anything about it. At about mid-afternoon, the screwdriver slipped. The upper beryllium half-sphere came into contact with the lower one, and the core sat in a critical configuration. The response was instant. The National Park Service account records a blue glow from ionization of the air and a wave of heat through the room. That blue light was not an explosion and not a sign that the core had come alive. It was a visible side effect of an intense radiation event that had already happened. Slotin knocked the upper shell away and ended the excursion. That stopped the configuration, though it could not call back the radiation already delivered. He took the highest dose. Others in the room were exposed too, at levels that depended on where they were standing. The record does not support turning this into a heroic scene stitched together from invented thoughts or last words. Some accounts stress that Slotin's position and his reaction may have limited what the others received. The verified core of it is enough. He was closest to the assembly when it happened. He removed the upper shell, and several people in the room were exposed. Slotin was taken for treatment and died on May 30th, 1946, 9 days later, at the age of 35. He was the second person fatally injured in a criticality accident involving the same plutonium core. The interval between the two matters. This was not a lesson lost across decades and rediscovered by a new generation of workers. Daghlian's death was recent, the warning was on the record, and the manual approach still had not been replaced. The witnesses matter for another reason. They show how a rule can be followed to the letter and still leave a dangerous process wide open. More than one person was there, but the physical arrangement kept the risk concentrated at the assembly. The safeguard was administrative rather than engineered, so it could improve observation and accountability without creating any distance. When the screwdriver slipped, no second pair of eyes could put the gap back before the burst. A sound criticality safety program needs procedures and hardware together, people checking one another, instruments that reveal changing conditions, and, above all, controls that keep those people outside the radiation field. None of that erases individual responsibility or turns the accident into a story where no decision mattered. Slotin demonstrated the hands-on technique that day, and the technical review records the configuration that made the slip possible. Two things are true at once here. Individual actions shaped the final seconds, and the design of the work decided that one person's final seconds could expose an entire room. The later move to remote operation went after the second larger problem. It changed the system rather than asking the next skilled operator to be steadier than the last one. The second accident also shows why experience cannot carry the whole safety load. Slotin was no uninformed visitor. He had run criticality tests and worked at the Center of Wartime Weapons Assembly. A system that depends on the hands of its most skilled operator looks safe right up until a tool slips. Skill reduces some risks, but it does not repeal gravity. It does not put physical distance between a person and a radiation source. And it certainly cannot call back a radiation pulse once the arrangement has gone critical. One more popular claim needs separating from the record. Some accounts say that Slotin deliberately used his body as a shield for his colleagues, and the National Park Service biographical page carries that interpretation. Other official accounts stay with the arrangement, the slipping screwdriver, and his position closest to the core. No surviving document preserves a statement from Slotin setting out that intention in the moment. So this case will not present a private motive as settled fact. What can be said is that his position gave him the largest dose and that he pulled the reflector apart. You can recognize what his death cost without inventing certainty the record does not have. The name Demon Core attached itself to the plutonium sphere after the two deaths. It works because it turns an invisible danger into a character. And that is also the problem with it. A demon implies agency, and the core had none. In both accidents, people built the configuration that allowed a lethal radiation burst. The two accidents were not identical. Daghlian was working with tungsten carbide bricks, and a dropped brick pushed the reflector arrangement into a dangerous condition. Slotin was working with beryllium reflector shells, and a slipping screwdriver let them close. The first happened at the Omega site, the second in a building later associated with Slotin's name. The equipment differed, and so did the immediate movements. The system failure underneath them was the same. Each time, the core started out in an arrangement meant to stay subcritical, with reflector material being brought closer to measure the approach to criticality. A small unplanned movement then took away the last margin, and the experimenter standing nearest had to reverse the configuration by hand after the radiation burst had already begun. That comparison is more useful than treating the two as separate freak accidents, because they were two routes through the same safety gap. The record does not show that everyone at Los Alamos was indifferent to danger. It shows a laboratory using a hazardous method during a stretch when the engineering transition to remote control was still unfinished. That is the lesson at the center of this case. A different reflector and a different immediate mistake sat on top of the same vulnerability. A human hand was the last safety barrier. Once that is clear, the nickname matters less than the operating principle behind it. A stable safety system does not require every participant to be perfect every time. It should be built so that a dropped object, a lapse in grip, or a misread gap cannot expose anyone at close range to a lethal burst of radiation. After Slotin's death, hands-on control of near-critical experiments of this kind stopped. Nobody banned the study of criticality, since scientists still needed measurements of how fissile systems behaved. What changed was how the experiments were run: distance, remote control, engineered disassembly, instrumentation and procedures that no longer treated a human body as the closest safety component. The Pajarito Canyon facility at Los Alamos was pushed toward completion. Later critical experiments that were run remotely from a control room roughly 1/4 mile away. That quarter mile was not a gesture. It changed the physical relationship between an experimental assembly and the people operating it. If a configuration produced an unexpected radiation burst, nobody had to be standing beside it to pull a reflector away. Controls, monitoring equipment, and plane separation built up layers of protection that did not rest on holding a screwdriver gap open by hand. Remote operation did not remove every danger attached to nuclear materials, and these two accidents did not by themselves produce every safety rule that followed. Claiming otherwise would be its own oversimplification. What they did become was a pair of standing warnings in the history of criticality safety, showing in human terms why geometry, reflectors, distance, independent checks, and engineered controls are worth the trouble. A laboratory cannot treat its most hazardous step as a test of personal steadiness and call the result safe. The move to remote work also corrected a false choice built into the older method. The options were never learn nothing or take reckless risks. Good science needs the measurement. Safety engineering decides how the measurement gets taken. A remote mechanism can bring components together under controlled movement. Radiation detectors can give warning. Automatic systems can interrupt or disassemble an experiment. And a separate control room can keep personnel out of range. Every one of those layers starts from the same assumption, which is that people make small mistakes and dangerous systems have to be designed so a small mistake does not turn fatal. The archive also sets limits on the story. 2 fatal accidents involving the same 6.2 kilogram plutonium core can be verified, along with the dates, the reflector materials, the dropped tungsten carbide brick, the slipping screwdriver, and the later move away from hands-on near-critical work. The record confirms that the core did not explode and that neither scientist died instantly in the laboratory. It confirms that the second accident came after the first had already forced safety revisions. What the archive will not support is the curse because the evidence points to physics and procedure. The core did not kill anyone by itself since the dangerous configurations came out of the experimental arrangements people built around it. No nuclear bomb went off in either laboratory because no such explosion happened. Nobody was forbidden from studying criticality after Slotin's death because the work carried on by remote methods. And the later illnesses and deaths that circulate in popular retellings cannot be counted as proven consequences of these 2 accidents without specific medical and documentary grounds. Some questions stay open. The public records do not preserve every private conversation or individual judgment, and they do not preserve the full internal decision sequence. that allowed the second manual demonstration to go ahead before the remote system was ready. This story stops where the sources do. Reconstructed dialogue, invented private thoughts, and supernatural claims would make a darker version of the case without making it any truer. The demon core was a dangerous material sitting inside a system that let one small manual error strip away the final margin of safety. Nothing supernatural was required. Harry Daghlian and Louis Slotin do not stand as warnings because they lacked skill. They stand as warnings that skill is no substitute for a system designed to protect people when skill, tools, and timing fail. If this case changed the way you hear the word safety, leave your conclusion in the comments, like this investigation, and subscribe to History Case Files for another record where the legend is not the same as the evidence. Next, open another history case file where an archival photograph tells only part of the story.